Okay, good afternoon for the people from Europe and good night for people from China. Welcome to attend the tonight's lecture by Professor David Fernández-Duque. First of all, we will give a brief introduction for the speaker. This is Professor David Fernández-Duque. He got his PhD in mathematics from Stanford University in 2008. His thesis is about the result in dynamic topological logic under the supervision of the famous logician Gregory Mintz. Since 2023 March, he is associate professor in the Department of Philosophy at the University of Barcelona. Before that, he holds several research positions at various universities, such as Ghana University, Academy of Science. Research interest. His research is in mathematical and philosophical logic, with a focus on the interplay between logic and dynamical systems. He has made many contributions to varied fields, such as proof theory, dynamical topological logic, model logic, probability logic, reflection principle, spatial and temporal logic, epistemic logic. Prize and awards here are just leave two. Ray Rater Best Paper Prize for his paper, The Topology of Surprise, in 2022. He won the Gödel Century Research Prize, awarded by the Kurt Gödel Society and the John Templeton Foundation in 2008. Our lecture will be live broadcast by Bilibili channel of the School of Philosophy at Wuhan University, and the Chinese audience can watch his lectures with the Bilibili platform. Okay, now let's welcome Professor David Duque to give his lecture. He will talk about the Goodstein works and the Gödel incompleteness. Please.
Well, thank you so much for the invitation and for this very nice introduction. I will now share my screen. So you should now see my slides. And let me just make it full screen. It's was it Control R? I forget. Because they changed the things around. Control. Oh. Does somebody remember the shortcut for full screen?
Yeah, you just make it first screen.
Yes, but what is a shortcut? Because they just updated Acrobat, and I don't know how to find it anymore.
On the right top, there is a on the right there is an item. Maybe you click that one. Is on the right.
I'm looking on the right.
This one on the right.
Yes.
Yeah, you can add Control plus L, and then you can make it first screen.
Control L. There you go. Okay, great. Thank you. Okay. Sorry about that. I get rid of this thing. So that like you said, the title of the talk is Goodstein Walks and Gödel Incompleteness. These are results with various people, most notably Andreas Weiermann, but there's a work with TCRI, with Stan Weiner, and we also have a PhD student working on this. I'll mention them as we go along. So let's first recall Goodstein's principle, introducing a little bit of notation that I'll use. So what's the idea here? You start with any natural number. We call it m, but for example, we can think that m is equal to 22. So what we're going to do is we're going to basically write this in binary, in base 2. It would look something like this. The novelty is that we also write the exponents in base 2. So normally this would look like 2 to the 4 plus 2 to the 2 plus 2. That's the binary representation of 22. But the 4 could itself be written 2 to the 2, right? So we get this hereditarily exponential form. And then what is the next step? We're defining a sequence. What we're going to do is wherever we see a 2, we put a 3. And then we subtract 1. So we're making a big jump and then a little tiny step back, right? This new number, I'm not going to try to write it down, but you notice that I started with 22 and suddenly have 3 to the 3 to the 3. That's 3 to the 37. That's got quite a few zeros. So it's a much bigger number. And this is, again, it's a sequence. At each stage, we do the same operation, which was we take the base that we're with, we raise it by 1. So now everywhere you see a 3, we have a 4. And we subtract 1. So again, a huge step and a tiny little step back. Now, what Goodstein's theorem says is that surprisingly, this will eventually become 0, which is very counterintuitive because it's growing so quickly. And that's all there is to the theorem. So this could be argued to be the oldest example of Gödel incompleteness that doesn't rely directly on coding or doesn't talk about meta-mathematical matters, but it's just simple operation in natural numbers, at least for a result, that still we cannot prove in PA. Now, in this talk, well, it's been many years since this Goodstein's result. This talk, we want to step back and look at it from a modern perspective. So the notation that we'll use here and the terminology are not necessarily what Goodstein used back in the day. The way we think of Goodstein today is it's made of several elements. First of all, we have a notation system for natural numbers. So I mentioned the exponential notation. Then we have a notion of normal form. So every natural number was written in terms of base 2 or base 3 or base 4 in a specific way, right? In this case, it coincides with the base k expansion of a number, except that we apply the base k expansion also to the exponents. And then there's a notion of base change where I say, well, whenever you see a 3, you put a 4. Whereas you see a 4, you put a 5. That's an operation on natural numbers that has to do with the way they've been written down in normal form. If we have these elements, we can define a Goodstein process. It could be a different notation system. It could be a different notion in normal form, etc. So with this in mind, in today's talk, I want to talk about Goodstein's theorem from a modern perspective with this terminology, this notation, and especially some new proof ideas. I will talk about the proof of termination. And then I will also talk about how to prove independence. These are some ideas coincide, but these are different things, right? One is the theorem is true, and one is despite being true, is not provable. And finally, I will talk about some recent extensions and generalizations. So we begin with termination. Oh, by the way, the term Goodstein walks is also has to do with some novelties that I will get to later. So we have a notation system. What is our notation system? We have terms. Our terms use 0. They use addition. They use exponentiation. Here, k is special because k is a base. So we're not going to mix bases. We're not going to have 2 to the 3 plus 4 to the. We're always going to have either things in base 2, base 3, base 4, etc. The base could change, but it'll be one fixed base at a time. Every term has a value. This is it could be written down in a proper inductive way, but it's pretty obvious what it is. It just evaluates what you see. And the base change operation intuitively is to replace k by L throughout. Here I will show you the inductive definition. So mostly base change is a homomorphism. So 0 goes to 0. It commutes with addition. The only thing the only place where we're going to change something is that if I see k to the something, then I will replace k by L, by the new base. So in the example, we begin with base 2 and raise it to base 3. So in this case, k will be 2, L will be 3. And we end up with a new term, which if before we had k's everywhere, now we have L's everywhere. All right, so now I don't know if I could, there you go, okay. So we have a notation system, meaning that we have a set of terms, but when we write down natural numbers, we said we're going to write them in base k. This is a specific way to write them. How will we describe it here? Well, 0 is 0. There's no other way to write 0, so that has to be the canonical way to write 0. How do we write a number base k when it's a positive number? Well, the first thing we do is that we find the biggest exponent we find. So you have some a such that k to the a, well, m is between k to the a and k to the a plus 1. This is a typo. It should be strictly less. That's going to be the first term. And then we write m equals k to the a plus some remainder b. And then we inductively write this b in normal form as is indicated here. Maybe the unusual part is that we also write the exponent a in normal form. So you can see when I move my pointer, right?
Oh? Yes.
Okay, thank you. Right, so this is an operation. The base change operation is defined on terms in principle, but we can apply it also to numbers by saying, well, if I start with a number, then I write it down in its normal form, and then I apply the base change. In this case, we have to indicate what base I want to begin with, because terms, I know the base of a term because it's indicated in the term, but natural numbers could be written in any base, so I have to specify, well, I write the number at base k in the canonical way, and then I replace k's by L. So with this in mind, we can define Goodstein sequences using our terminology as follows. And we start with some natural number, any number that you want. The first element of the sequence is just that number. And at each stage, we do the following. We have our number written in some base. We raise the base by 1, and we subtract 1. This plus 2 and plus 3, maybe it looks a bit strange, but just think that we cannot write numbers in base 0. Base 1 also doesn't really make that much sense, so we begin by writing numbers in base 2. So when I is equals 0, we want to already have a 2 here. That's the only reason that I'm adding the 2 and the 3. The important part is that the top base is 1 more than the bottom base. So we keep going, and finally we reach a 0, and then the sequence just terminates. And that's the length of the sequence. In principle, we could imagine sequences could be infinite, so we allow for the length of the sequence to be omega, if that is the case. And then the theorem is that for every natural number, there will be a certain I, which makes the sequence be 0, or in other words, that every Goodstein sequence starting at any natural number is 0. Now, I'm going to give a very rough sketch of the proof. And, well, I'm going to give a very rough sketch of the, let's say, old-fashioned proof, and then I will talk about how we are proving it these days. The proof goes by transfinite induction. So just a quick reminder of ordinal arithmetic. Ordinals are canonical well orders. They can classify it in 3 types. So you have 0, you have successors. So basically you have 0, 1, 2, 3, 4 are all successors. Then you have the limit of those, omega. That's a limit ordinal. And in general, every ordinal that you create from there on is either going to be a successor or a limit ordinal. We usually these unions, we write them like limits. And if you want to define something recursively on the ordinals, you have to take care of these 3 cases, right? So the usual arithmetical operations can be extended to the ordinals, addition, for example, where these first two items should be familiar. This would be what in PA or similar systems you would use to define addition. And you have to add, well, what do I do to limits? And the rule will generally be we're going to make limits, make the operations be continuous on the right. So this, if I add a limit to an ordinal, and the limit being on the right, then I just take the limit of the values. You can imagine here that this will not be commutative, and in fact, it's not continuous in the first argument. But that's, well, it is what it is. You're not going to get all of the properties that you have from natural numbers, but you will get many of them. Multiplication, same idea. You have these two are going to be the familiar recursive definition of multiplication, and you make the operation continuous in the right entry. And exactly the same idea for exponentiation. And you could generally take other arithmetical operations, like super exponentiation or so forth. As long as they're defined recursively in the natural numbers, you should be able to find an analog on the ordinals. Now, I mentioned that after the natural numbers, we have the first limit ordinal. We write it omega, and then this guy is going to be important. If you look at the operations we have here, we have addition, we have multiplication, exponentiation. If we try to write down ordinals using these operations, the biggest, the fastest growing operation is going to be exponentiation. So you just keep applying it to omega. You're going to get a sequence that bounds anything that you can define in terms of these operations. And the limit, the first thing that you cannot write down using addition, multiplication, and exponentiation is epsilon 0. That's well, that's just what it's called. Now, the basic operation I talked about, if you, as I said, if you have a recursive definition, a lot of times on the natural number, so a lot of times it works out on the ordinals as long as you basically choose what to do in limit cases. Also, something similar happens to the base change. There's no reason why we can't apply base change where we take a term in base k and we replace the k by omega, or actually any infinite ordinal. The only thing that we do is that now when we replace k by the new base, well, the new base is omega. And because all of the operations we're using make sense with base omega, then this is a perfectly fine new number. It's a generally infinite number, but that's fine. And as before, these are operations on terms. If I have a natural number, then I first write it down as a term, and then I apply the base change, right? So I said I was going to give a very quick sketch of the original proof before I go on to the version of the proof that we're working with these days. What was the idea? So this is a sequence I showed you at the beginning. This is 22, and then the first few elements of the Goodstein sequence. And I'm going to apply the omega base change. So this would become this ordinal here. This second one, again, every time I see a base, the base in this case is 3, it becomes a new base, which is omega. And now I notice that even though the second number was much bigger, I'm getting a smaller ordinal, right? Because 2 is less than omega. Then it becomes 1. You can imagine that as I continue the sequence, I will I get a 0 here, and I start to attack this second term. Eventually, because this is there is no infinite descending sequence of the ordinals, eventually the ordinal values I get have to reach 0, and that means that, well, since the sequence on the right has to be finite, the sequence on the left also has to be finite. That is a proof idea. And that requires a property that if I decrease numerical value, so when I go from a number to a number -1, I also decrease the ordinal value. That's going to be true, but we're actually going to prove something stronger, and it's not obvious right now that it is stronger, but we'll get to that. So we're going to prove that the base change has this sorry, not the base, well, the base change together with normal forms have this very specific property, and the idea is as follows. Suppose that I take a term that may not be in normal form, just some expression made up with addition and exponentials, and I raise the base of it. Well, we're always going to get a value that is bounded above by what we would get if we had taken the normal form. And this, you could take it as an exercise. It's not that hard to prove, or you could just look in the paper. It's not that hard to prove once you know what you're trying to prove, right? So the property itself is maybe not that obvious, but when you say, oh, the normal forms give me the maximal value when I apply base change, then you could sit down and check that is indeed the case. But just to convince ourselves by an example, I'm not going to get into this proof. It's calculation. Things work out. But I will give an example just to illustrate. So if I take the number 8, the normal form of 8 is 2 to the 3, which I would write 2 to the 2 plus 1 because 2 plus 1 is in base 2. I could also write 8 as 4 plus 4, which would look like 2 to the 2 plus 2 to the 2, right? Now, if on the left side I apply the base change operation, I get I replace the 2's by 3, so I get 3 to the 3 plus 3 to the 3, which I can simplify to 3 to the 3 times 2. That's going to be a smaller value than if I start on the right side and change the base, because this plus 1 is basically multiplying things by 3. And again, this is an example, it's not a proof, but it gives a little bit of a flavor of why having the choosing your exponents to be as big as possible, which is what our normal forms do, tends to give a bigger blow up when we do base change. Now, once you've done this proof, which, as I said, is maybe a little bit tedious, but things will basically be working out, and you go back to it and you read it again, you will notice that, oh, it actually would work even if I'm looking at trying to find a base change. So the normal forms, what you have on the right, the normal form of m, if I apply the ordinal base change, will also give me the maximal possible value among all terms that give me n. So that's, if you do a few examples, it looks like it's true, but it's a little bit of an exotic property. I would say it's more exotic than the monotonicity that a bigger number gets a bigger value after base change. Fine, but it is a stronger property. So why is it a stronger property? Well, it implies monotonicity by a pretty simple argument. So what do I mean by monotonicity? I have one number that's less than another. I apply a base change. Well, the bigger number will get the bigger base change, right? And we use that in our proof because we want the ordinal values to decrease whenever we subtract 1. All right, so we are assuming already that we have the maximality base change. So what we're going to do is we take this number, n plus 1, and we want to check that its value under base change is greater than that for n. And we know that if I write n plus 1 in normal form and I apply base change, I will definitely get it. Well, I will get something that's at least as big as any other way to write n plus 1. Well, one way to write n plus 1 is write it as n plus 1 and just compute the normal form of n itself, and then just plus 1 at the end, right? So I write it as k to the 0 because that's the way 1 looks in our notation system. So this is a term that has value n plus 1. Therefore, whatever value it gets is bounded above by by applying base change to the normal form of n plus 1. So we have this first inequality. Then we just compute this. So this, all right, so if I apply base change here, I still get a 1 because k to the 0 gets replaced by l to the 0. That's 1 either way. And so that's just the base change of n itself plus 1. And thing, yeah, these should not have the bottom k, but it's because they're terms. It's not a big deal. So yeah, indeed, if I apply base change to n plus 1 written in normal form, then I get something bigger than if I apply base change to n written in normal form. So we have this monotonicity property. And as before, once you've done the proof, you say, hey, this also works for the infinitary base change. So the ordinal interpretation of a smaller number is smaller than the ordinal interpretation of a bigger number by literally the same argument. Okay, so what do we get from monotonicity? We also get this. This is a little bit of a technical property, but this is, I would say, the last technical property we need to do a proof of Goodstein's theorem, which is basically that if I take a term and I raise the base, and my first term was a normal form, then the second term is also a normal form. And here you can see that this is the case. So to check that a term is a normal form, I just need to check that the exponents are decreasing, and that the coefficients, there's no coefficients here, they're all 1. But if I do have a coefficient, it just has to be less than the base, right? So that's how we write numbers in base k. And this follows very easily from monotonicity. So we have a number written in base k like this. So it's k to the some big exponent times some coefficient plus k to some slightly smaller exponent plus some coefficient, etc., etc. And since we know that the base change operation is monotone, then indeed the exponents are in decreasing order. And the coefficients are indeed less than the new base, simply because the new base is bigger. So actually, this is the step where you notice that you can change the base to a bigger base, but if you start changing it to a smaller base, you actually could have some trouble, and generally will not have a terminating process. In fact, you could change the base by a much bigger base. Changing the base to the base plus 1 is only one of many choices, and it doesn't affect the proof at all. All right, so we get this corollary. So what does it say? So take a number, write it in base k in normal form, and raise the base to omega. Do that, and then on the other hand, take the same number, write it in base k, but then raise it to base L, and then raise that to base omega. So you kind of break it into 2 steps. Well, you're going to get the same value. Why? Well, when I raise this, I get something that's already in normal form, and if I just think of k or L as a symbol, I get the same symbolic expression. So if I plug in omega, it doesn't matter whether I had k's or I had L's before. But that only makes sense if the result of this operation is in normal form, which is what we have up here. All right, so now we're ready for the proof of Goodstein's theorem. So you start with some natural number. The first element in the sequence is m. This is just a reminder. And you recursively generate new numbers by saying, well, I take my previous value, I raise the base to 1 more than the base I already had, and I subtract 1 to the result. And that's the next element in the sequence. The theorem is that at some point we reach a 0. So what we're going to do is we're going to look at the ordinal interpretations. Now you see I plus 3 here. Why? If this term is in base I plus 3, then the natural thing is to change from base I to 3 to omega. And this is, there's a typo, there should be an M here. Okay, so here I'm only plugging in the definition. Gi plus 1 is the old one with base change minus 1. Just plugging that in. We know that the base change is monotone, so this gives me a smaller value than if I did not subtract the 1. We have a base, we have normal form preservation, meaning that this new expression, when I raise the base by 1, is still a normal form, so raising the base again will give me the same result. So I could just go ahead and start from the original base and go all the way to omega and no problems. And then we're done, right? Because what are we seeing here? If we take the respective elements of the Goodstein sequence and we we raise, well, we take in the base that it's written in, and we raise that to omega, then we get a decreasing sequence of ordinals, and that has to go to 0. So, like I said, we had some extra work because we proved not just that we had monotonicity, but also that we had base change maximality. Why did we do that? Well, you could say, well, it's kind of interesting that we have maximality, and sure, it is. It is interesting, but actually, we also get a very nice additional result. And this is everything I talked about so far was a version of a proof for Goodstein's original theorem. Now we're going to talk about a new result. So what is a Goodstein walk? What we're going to do is we're going to throw this idea of normal forms out the window. You have a sequence of natural numbers. You start with whatever number you want. And at each point, what are we going to do? There's no normal forms here. You just take your number, you write it down however you want, term, and then to that term, you apply the base change. So this tau I, sure, it could be the normal form of m, but you could also write m as just 1 plus 1 plus 1 plus 1. So it would be k to the 0 plus k to the 0 m times. You could do some sort of in-between thing. Anything you want, write down m as a term, raise the base, subtract 1. And then at the next stage, just use an entirely different criterion to just assign a completely different term to the next element in the sequence, raise the base, subtract 1. As before, the rule is that once we reach a 0, we stop. So the very surprising theorem is that every Goodstein walk terminates. So not just every, well, it was already surprising that every Goodstein sequence terminates. But it's even on top of that, it's surprising that the normal forms were not essential. You could just literally write down the numbers however you want, as long as you have addition and exponentiation as your basic functions. Just write down numbers in any way you wish. Apply the Goodstein sequence base change operations, and you're going to get finite sequences. So let's prove this. And once you see the proof idea, it starts to become much more transparent, because what happens is that the original Goodstein process, where we take the normal forms, is majorizing any Goodstein walk you could come up with. So your Goodstein walk is going to be bounded below by the official Goodstein sequence. How does this work? All right, so we start with a natural number. The first element of the Goodstein walk is a natural number. The first element of the Goodstein sequence is the natural number. So yeah, we have the same value, right? There's nothing here to talk about. So in the inductive step, you have your value, your current value. You write your number as a term. You raise the base of the term to the next value, and you subtract 1. So this is by maximality of base change. We have that if I write the number in normal form, so that's what this bottom I plus 2 means. I write it in I plus 2 normal form and then raise base, I get the maximal possible value. By induction hypothesis, this is bounded by the official Goodstein sequence, and that is just what gi plus 1 is, right? So this operation gives you the next element of the standard Goodstein sequence, and by following the inequalities, whatever term you came up with on your Goodstein walk is going to be bounded by the official value. So there you go. So because the Goodstein sequence is finite, any other Goodstein walk is also finite, because when you reach 0, you already must have reached 0 on the walk. It's curious. It also has a nice use that I will talk about later if I get to the last topic, which I think I will, because we have plenty of time. But first, let's talk about independence. Now, we talked about numbers being in normal form. Ordinals could also be in normal form. The idea is exactly the same. So you're going to write omega to some exponent plus omega to some other exponent and so forth. This time we don't have any bound in the coefficients. So basically, so I could have omega 2 to 3, and I could have 100 copies of that omega 2 to 3 times 100. That's fine because 100 is less than omega, right? So the big difference between anti-normal forms and base K representations is that we don't have this bound on the coefficients, unless you consider omega to be a bound. But aside from that, it's pretty much the same idea. And I mentioned these because for this part of the talk, they're going to be very relevant. For the first part, maybe they were not so much. Now, we have limit ordinals, and there's any limit ordinal can be written as limit in many ways. So just to give an example, you have omega. Well, it's the limit of n, 1, 2, well, 0, 1, 2, 3, 4, etc. It's also the limit of the squares of the natural numbers. That grows a little bit more quickly, but at the end of the day, you're reaching an infinite ordinal, so it's not really going to affect you that much. Or an even more quickly growing sequence. Or you can even do some slower growing sequences. You could stay at 0 for a while and 1 for a while. As long as you're getting to omega and not passing omega, you can knock yourself out here. But sometimes for certain things, we want to choose a canonical representation, right? So we want omega to be this limit and not this limit in some sense. So this is what we call systems of fundamental sequences. They're just, look, I'm going to choose once and for all what sequence approximates my limits. This is something that could be done if you're below computable ordinal. So if you were below epsilon 0, we could do this systematically. You can well, let's just say that it becomes less and less constructive as you go to beyond computable ordinals. But epsilon 0 is a nice computable ordinal. We have no problem to define such sequences. We want to define them in a specific way that is nice. And I will show it to you in its natural, and then I will say what properties it has. And some of the design choices in the specific sequences we use are actually required, even though they seem unimportant. So let's start with the basics. So fundamental sequences approximate limits, but what if you have something that's not a limit? We still want them to be defined. So 0 just stays at 0. There's nowhere else to go. 1 goes to 0. In general, successors will go to their predecessor. That's, let's say, the most reasonable value. If we have a sum, then we just apply the fundamental sequence on the right, which makes sense because remember that addition is continuous on the right, but not on the left. Now, for this expression to have a well-defined value, we have to have this in normal form. If you don't, you might be able to fiddle a bit with the end result. So first you write it in normal form, and then this operation is well-defined. All right, so this maybe becomes more transparent when you think of alpha equals 0. So we said that omega, which is omega to the 1, is just the limit of all natural numbers. We do a +1 because we want to start at 1. Why is that? I don't think there's an easy way to explain aside from the fact that the following properties we need just will not work if we don't put this +1. So sometimes ordinals are just finicky like this. And again, exponentiation is also continuous in the right-hand argument, so we just apply the fundamental sequence there. So these have the property, and you could prove this, but you could also convert yourself by doing a few examples. That if you have a limit ordinal, then the limit is the limit of the values of the fundamental sequence. So again, in the case of omega, we're here with alpha equals 0. Here you also get a 1. So indeed, omega is the limit of natural numbers, right? So you could check that this also works more generally by some induction. So why do we want such a canonical representation of everything? Well, when you have so much control over an ordinal, then you can use it in some recursive definitions that maybe would not make that much sense if you're allowing limits to be represented in different ways depending on your mood uh, or any other circumstance. So let's see, how do these fast growing functions go? So we have for every ordinal below epsilon 0, we're going to define a function h alpha. H alpha is a function in natural numbers. Each individual h alpha is going to be increasing. Bigger alphas will give bigger functions, not necessarily pointwise, but in the limit. So if beta is greater than alpha, then h beta will eventually bound h alpha. So how do we define these? Right, so you have two ordinals less than epsilon 0. Alpha is arbitrary and lambda is a limit. What the function will do is h0 is the identity. Maybe that's probably what one might expect. Successors are only going to add 1 to the argument. And in limits, what I do is I say, well, suppose that by transfinite induction, I imagine that the functions h lambda prime are defined for every lambda prime less than lambda. In particular, I could evaluate at these values. So I say, well, if I have a value x and I have a limit here, I replace lambda by its fundamental sequence at this stage, and I add 1. So what are we doing here? The more natural case to think about is when x equals 0. So if x equals 0 and you start at some ordinal alpha, this function is counting how many steps you need to go down the fundamental sequence to reach 0, because at each stage you're just adding 1 and getting a bigger and bigger argument until you reach 0, and then this x that you have here is just counting how many steps it took you to get down to 0. Now, this function in principle was defined below epsilon 0, but epsilon 0 can itself be given fundamental sequences. So we said that it was the limit of these towers of omega. And this tower of n omegas is called omega n. That's just notation. So now that we have fundamental sequence also for epsilon 0, then this function is defined also for epsilon 0. But more generally, if you take any other big ordinal and you start to also define fundamental sequences below it, then we can extend these functions to those ordinals as well, right? So they're not uniformly defined ordinals, but once we settle on okay, we want to look at this ordinal, we want to have this system of fundamental sequences, then that's then the function is well defined by these properties. So excuse me 1 second. Sorry, I have a bit of a cold. All right, so right, so what is the point of these functions? If you've taken a course in proof theory of Gödel style analysis of P arithmetic, you know that epsilon 0 is the ordinal of PA. It's the ordinal of PA in many precise senses. So it's, for example, the pi 1 ordinal, meaning that it's the limit of all ordinals up to which I could do transfinite induction. It's also what we call the pi 1 ordinal, which controls the computable functions that are provably total. And in this case, h epsilon 0 is a function that grows faster than any computable function that PA proves to be total. What does this mean? Well, evidently, if I plug in a small value, if I compute h epsilon 0 at 0, I might not necessarily get a value that's so huge, or maybe I will. Maybe it's already a huge value. But I could always choose a function that has a bigger value. F of 0 is greater than h of epsilon 0 of 0. Sure, I could do that. But eventually, after I wait enough, h epsilon 0 is still going to beat that f that I chose. So any provably total computable function of PA is majorized by this. And this is one of the fundamental tools that we have to prove independence statements. If you have a theorem that somehow forces something to exist that grows faster than this function here, then you know that whatever your theorem was is not a theorem of PA, or at least that somewhere in the chain of implications to get to this function f, you use something that goes outside of PA. And this is what we're going to do for Goodstein. Now, I said that the fundamental sequences were selected in a specific way. This is the inequality that we need. Like I said, it's a bit finicky, and if you slightly change some things that look innocuous, you might ruin this property. So what does this property say? I have an ordinal, and I'm seeing I should have this 0 here should be an n. This should be an n. These are n's, and this one is in fact a 0. So basically, if I have an ordinal and I have an element of its fundamental sequence, and I have some ordinal here in the middle, then this is sort of trapped in the sense that if I apply fundamental sequences, I stay in this interval. I stay in this interval until maybe I hit the bottom itself, and only then can I escape. So this allows me to control really what's going on in this interval between an ordinal and its fundamental sequence. And as we'll see, it's very useful for proving some inequalities. So let's say that we have some system of fundamental sequences satisfying the Bachmann property. It doesn't have to be this one. It just assigns sequences that converge to limits and so forth that happens to satisfy this inequality. Again, this should be an n. Then this allows me to bound the h functions in a very specific way. So I take a sequence of ordinals, right? The sequence of ordinals is decreasing, and eventually it'll become 0. But it's decreasing in this specific way that it decreases less slowly than the fundamental sequences. So psi 0 is between some psi and its fundamental sequence at x. And whenever I do one step along the psi sequence, then I get something that's bounded below by if I had instead gone down the fundamental sequence. So notice that this is a very local inequality. I'm only comparing the psi n with psi n plus 1. I'm not, I don't look at the sequence globally. I never compare psi 3 with psi 100. I'm only looking at psi 3 and psi 4, psi 10 and psi 11, and that's it. And well, yes, so this sequence is 0 at some point. And the point is that if I have this completely local inequality that only compares one term with the next one, then the sequence, if you ignore the x for a second, the length of the sequence is at least the value of the h function for this ordinal that we had here. This x is just the initial value, so if x was not 0, then I just have to add it. So it's here you can imagine as when we add x here, you can imagine that we already had some elements at the beginning of the sequence and we're starting a bit late. So you can imagine there's a sequence of length L plus X somehow implicit in this computation. Okay, so this is great, and this is why we want fundamental sequences with a Bachmann property, because now by doing a very simple, well, maybe simple is not the right word, but a relatively simple local computation, I can obtain a global comparison of the sequence with the Hardy functions. And that's what we're going to do for Goodstein. And if you master this technique, you can prove that all kinds of things are independent of PA. So the lemma, okay, so what is my sequence? My size would be the ordinal interpretation of the elements of my Goodstein sequence. So what I do here is I take some natural number. I imagine that it's written in base k plus 1. So if I write the number in base k plus 1 and I take its ordinal interpretation, that is bigger than if I start with n plus 1. But as we know, it's monotonicity. What we don't know is that, okay, so this is a bit smaller, but it's not that much smaller. In particular, the fundamental sequence gives me a smaller value. So if I start with this big guy and I compute its fundamental sequence at k, I get something that is equal or less than what I get by subtracting 1 in the Goodstein process. This will look less mysterious with an example. So this is plugging in some numbers to this lemma. If m is 3 to the 3, the lemma claims that this value is less or equal. What is this value? So if 3 to the 3, I subtract 1, I get this number, and this should have parentheses, so the operation is being applied to the full number. And that is less than the original number, 3 to the 3. So let's check it by computing the ordinal interpretation and see that it's actually true. So what does fundamental sequence do? To limits. So here I apply the fundamental sequence to the exponent, right? Because remember, it's continuous in exponents. And that is bounded by the value of taking this whole term. So when I subtract 1, I get this piece here that I was going to get anyway, and then I get a tail that you get from expanding the subtraction of 1 to an exponent. And then this is bounded below by the value of taking this one and raising the base to omega. Right. Right, so this, again, once you know what you're trying to prove, if you do it as an exercise and just try to prove it, it'll come out. And if not, you could just look at it in the paper. So, all right, so let's give a notation to this. So what is this? Remember the Goodstein process, it's a natural number, and you start to do some operations so that eventually reaches 0. So it reaches 0 at this number. So this G infinity is just how long do I have to wait to reach a 0. And well, using these inequalities we have and so forth, we can check that the Hardy function is bounded below by this termination time of the Goodstein process. And let me, okay, push the wrong button. So give me a second. Where are we? Right. It's just an instance of this theorem because my ordinal sequence, the size, are the ordinal values of the Goodstein process, and we're just writing down this version of this inequality. And that's what we have here. Okay, so that gives me some hope of proving the independence, because I'm in a certain way I'm bounding the Hardy function by the termination time of the Goodstein process. If PA would prove that this termination time is actually a finite number, then I should not be able to have such an inequality in general. There is one last step of checking that it actually does yield a function that is faster growing than h epsilon 0. So if PA proved that this was always finite, then in particular, these guys are finite. So 2 to the 2n, I guess it's not 2 to the 2n, but 2 super exponential 2n. That's a tower of 2n2. So that's a big number, but PA could handle these big numbers. If I try to write down in base 2, the only thing I could do is actually write down the tower of exponents. There's no other way to well, it's not that there's no other way, but that's precisely going to be the base 2 representation of this number in normal form. And then when you compute the ordinal interpretation, you still get a tower of 2n omegas, because that's you're used by omegas, right? Now this number is actually a little bit bigger than it needs to be, but it makes it easy to convince yourself that this inequality will hold. Basically, when we kill the first n of these, we are raising the inner part to n plus 1. And then we're still left with n omegas. And you actually get a much bigger value than what I wrote here, but it's not hard to convince yourself that you at least get that. So okay, so we're doing some good progress, because this is precisely the value of h epsilon 0 at n. And well, so putting all this together, we did manage to produce a function. I think, let's go back here. If I combine this inequality here with this inequality here, I see that my function f gives an upper bound for h epsilon 0. So that means I cannot prove in PA that this is a total function. All right, so that's independence, and I promised some extensions. So I already talked about Goodstein walks. Goodstein's theorem was specifically for the Goodstein sequence written in normal form. Goodstein walks, on the other hand, don't rely on notion of normal form, and they're still terminating. So that's one novelty of that we added on top of Goodstein's theorem. There's another direction that you can go in. So if you remember the first few slides, we said that a Goodstein process depends. Well, you have the notion of normal form, which we now see is optional. You have the notation system, which are some terms representing functions that you use to write the natural numbers. And okay, so the basic Goodstein process is related to exponentiation, but we have much faster growing functions on the natural numbers. So let's start with one. Okay, so you could do something intermediate, and you could say, all right, so what goes after exponentiation? Well, you have super exponentiation. Yeah, you'll get a slightly stronger Goodstein principle in this fashion. But let's do something that grows systematically faster. So if you go to the Ackermann function is one of the best known examples of computable functions that are not primitive recursive. And it's, if it doesn't exactly give super exponentiation, it does give something at about that level of growth, and at the level of growth of iterations of the super exponential and iteration stat and so forth. So it's a little bit more of a systematic way of producing functions that grow quickly in the natural numbers. And when we did the original Goodstein process, we had the notion of base. We have the base k. So we write things down in terms of base k exponentiation, and k could vary. So to have a proper Goodstein process in this Ackermannian context, we're going to also need to have some notion of a base. So this version of the Ackermann function has the usual A and B work as in maybe the more familiar version of the Ackermann function. And this k, we think of it as the base. Right, so if to give a nice definition, I'm going to define this auxiliary value. Just if I ever have to evaluate the functions at -1, the answer is 1. So now let's define the Ackermann function recursively. We want to start at the exponential. Just think of it as expanding on the previous Goodstein theorem. So the exponential has to be there at the first layer, and then we're going to go to faster and faster growing things. So what do we do for bigger values of a after 0? Well, the a plus 1 branch of the Ackermann function, what it does is iterate the a branch. Now, in a standard Ackermann function, you would have one iteration here, and as you expand it, you notice that you will have b iterations of the a branch of the Ackermann function. But our base k we wanted to affect things, so now instead of applying k iterations, well, one iteration will apply k. So if I keep expanding this until b becomes 0, I notice that I have k times b iterations of the a branch of the Ackermann function. So this is something very similar to what we'd expect in passing from exponentiation to super exponentiation, right? Now, our term system will be built from these operations. We have dropped the standard exponentiation, but we still kind of have it there because exponentiation is just a 0 branch of the Ackermann function. So this can be viewed as a proper extension of the Goodstein notation system. And we have a base change operation, whereas as always, it's a homomorphism in addition, and the base that we change is the parameter here, which we often don't write it down just to make things look nicer. And so when I raise base, well, first of all, I'm also going to be looking at an exponential based on L and then on K. But we also change that every time I iterate a branch of the Ackermann function, I iterate it L steps at a time instead of K steps. So you can imagine that by passing to a bigger branch, I just get things that grow much, much faster. Now, I'm going more quickly than I expected, so I didn't want to define this. But I think I have time. So yeah, if you excuse me, I'm going to go to a different PDF that has a. No, I'll tell you what. I'll go back to this later if we have time at the end. I think that's a better idea. So in these slides, I don't describe this. I do want you to know that this is this normal form assignment based on the Ackermann function is actually very, very complicated. So what will you normally do? So you want to write some number in normal form based on the Ackermann function. So you're going to want to have a leading term that looks like Ackermann AB. Normally, what you'd expect to do is to just maximize A. So the bigger branches are growing faster than the smaller branches. So the bigger this little A is, the bigger branch you're in. And then you just find the biggest value of B for that fixed A. This sounds almost the same as what we did for the exponential number forms, but actually that straightforward way of writing down numbers is not going to be the maximal assignment. The maximal assignment is the sort of well, we call it the sandwiching normal form. So you sandwich numbers in better and better approximations. It's very complicated. I actually want you to think that it's complicated because that is going to make our results seem nicer in a way that you will see soon. But okay, so we have the Ackermannian terms. We have somehow written them down. We have somehow used them to write down natural numbers. And as before, we want to interpret them using functions on the ordinals. Now, epsilon 0 was based on the ordinal versions of addition, multiplication, and exponentiation. So we want the ordinal version of the Ackermann function. So what is that? If you have a bit of a background in proof theory and you went beyond PA, you probably have looked at these. But if your background in proof theory is basically an ordinal analysis of PA, then these are the next step in ordinal notation systems. So Veblen functions are based on normal functions. What are normal functions? You take any function in the ordinals that is increasing and continuous. So it's about as vanilla as you could be within the realm of ordinal functions. So what are examples of increasing continuous functions? Well, there's of course the identity will always have all these properties. If you multiply times 2 on the left, for example, 2 times psi, that's going to be increasing and continuous. So remember that multiplication, addition, things like that are continuous on the right-hand argument. A little bit more interesting, omega to the psi is a normal function. So this is basically it is the ordinal exponential. It is increasing as one would expect from the natural number version, but it's also a continuous function. So that's some nice novelty we have. Now, take a closed unbounded class of ordinals. So closed means topologically closed if you generate topology based on limit ordinals. So if I have an ordinal and I have any sequence converging to it, then that ordinal should also be my set. Unbounded means that I have an element bigger than any ordinal. So if you have a nice set of ordinals like this and you enumerate them, you start at the first one, then you jump to the second one, then third one. At step omega, you take the first limit and so forth. Then you're going to get a nice enumeration. A nice normal function. And all right, so you look at your normal functions and you're trying to solve this equation, f psi equals psi. Well, that's not going to be that hard to solve because you start taking iterations of f, and you realize that what you get to has to be a fixed point. So the limit of psi followed by f of psi followed by f of psi and so forth, it converges somewhere simply because it has it's increasing and it has a bound, and then you just check that somewhere is a fixed point of the function, and then by being a little more careful, you realize that these fixed points are unbounded. And why are they closed? Well, since the function is continuous, if I take a sequence of fixed points that converge somewhere, then that thing must also be a fixed point because that's just how continuity works. Okay, so now that we have this background, that normal functions have fixed points and closed unbounded sets give normal functions, what you do is you say, all right, so I'm going to start with a base function, and this already might smell a little bit like the Ackermann function that we have, because remember that the zero branch of the Ackermann function was just the exponential. So we start there, and we say, okay, so we have this nice normal function, omega to the psi. That has some fixed points. What we're going to do is make phi 1 just enumerate the fixed points of the omega exponential. It's not on the slide, but if you take epsilon 0 and you try to raise omega to the epsilon 0, by checking the definition, well, you have increasing towers of omega, so now you have towers of omegas with one extra omega. That's also going to be epsilon 0. So epsilon 0 is the first value of phi 1. And epsilon 0 used to be the big guy, so now we very early get epsilon 0, and from there are going to be building up to bigger and bigger ordinals. And how the limits work, well, you sort of check that we have a limit ordinal, then the joint fixed points of the things below it are also going to be closed and unbounded, so you enumerate those instead. So the moral is that if alpha is less than beta, then for any gamma, phi beta of gamma, it's a fixed point of phi alpha. So bigger values are fixed points of the smaller values. Now, I'm not going to get too much into this. This is a little bit of just a technical point. If we don't want our Bedlam functions to have fixed points, then you can do that. You basically, if you're reaching a fixed point, you skip it and you keep going. So we actually are going to work with those. Why would we work with those? Well, it's very simple. So the Ackermann function doesn't have fixed points. So trying to interpret it as a function with fixed points will get us into some trouble. So now, how do we do the base change to terms that have the Ackermann function? Well, as usual, we're going to have a homomorphism on addition, and the Ackermann function now will become this fixed point free Veblen function. So this result, it's really in two papers. The first paper, we showed that for these sandwich in normal forms that I did not want to define, these Goodstein sequences are finite. The second paper, that's a recent paper with Andreas. I think it's not even accepted for publication yet, but it's in the archive. We have that every Ackermann and Goodstein walk is finite. Why would that be? It's here. No. Why would that be? Well, once you have maximality under base change for your normal forms, then the arguments that we gave before, that's saying that the Goodstein process that follows the normal forms is going to give an upper bound for any other Goodstein process. That argument goes through, and therefore, if you can prove termination of the maximal base change maximal normal forms, then you automatically have termination of any other Goodstein walk that you could come up with. So what independence results do we get here? I don't know everybody's background here. If you've taken a little bit of studied a bit of second order arithmetic, one of the first one of the important theories that you come up to is arithmetical transfinite recursion, which is misspelled here. So what does this do? There's a couple ways to think about it. One way to think about it is, well, you have a second order extension of PA, right? So by being second order means that you can reason about countable well orders because you code them as second order objects, as sets of natural numbers. And then you have an axiom that says something like the following. You say that, well, if lambda is an ordinal, then the lambda Turing jump exists. That's if you're coming more from computability, you might think of it this way. If you're in proof theory, maybe you think of it more along these lines. So you have some arithmetical predicates. It depends on n. It also depends on a set x. But when you say that the predicate is arithmetical, it could mention sets. Yes, sets could be involved, but it cannot quantify over sets. So you can't have no second order quantification. You only have quantification over natural numbers. All right, so you have such a predicate. You have a well order. Then you could recursively apply the predicate to the layers of a new set in such a way that the new layer is obtained by applying the predicate, by checking whether the predicate holds an n with the previous layer as the parameter here. So it's just an arithmetical definition, some arithmetical formula, but iterated along a transfinite well order. And arithmetical transfinite recursion just tells you that there is a set that has these properties. Okay, so what is the proof theoretic ordinal of arithmetical transfinite recursion? Well, this was known as gamma zero. So what we're going to do now is the five functions have been looking for fixed points on this rightmost argument. Now, in general, we might not always be able to find fixed points here, but for 0, if we fix the right argument to be 0 and we start to look for fixed points on the left argument, then you could check that that's also a normal function. And therefore, well, once again, we have all the fixed points we want. And the first one is going to be gamma 0, and that's basically the smallest ordinal that you kind of write down using addition and these Veblen functions. Okay, so this is the ordinal of ATR naught, which means many things, but in particular, it means that that ATR naught cannot prove totality of this function. So what does this mean? Remember that to have these faster growing hierarchies, we have to first settle on systems of fundamental sequences. Now, I'm not going to do that now. I'm just going to mention that there are natural sequences of fundamental sequences for gamma 0, and they can be made to also have the Bachmann property. And once you've selected your system of fundamental sequences, then the recursive definition I showed you before just automatically gives you a family of functions. And when you do that, then it's, let's say, folklore in proof theory, or not at all easy to check, but follows a bit from a Gensen style analysis, but that that you cannot prove that these functions are total in ATR naught. So what we do here when we're doing working on Goodstein is usually take the results like this at face value. Somebody's already done the proof theory. We believe the proof theory. We're going to use that to show that new things are also independent. So this result for us works as a black box. So if you read the paper, the paper on proceeding of the AMS that works on this, then this result is just like, look, we know this, let's work with it and see what happens. And when I said that ATR naught does not prove that this is a total function, you get something stronger like before, that H gamma 0 majorizes any function that is provably total, and therefore ATR naught does not prove that the Ackermannian Goodstein process terminates. Okay, so the proof idea is very, very similar to what we already talked about. Things get much trickier now with the bigger ordinals, but the heart of the proof is the same. And so, as I mentioned, I'm ahead of time. So I think I'm going to do a couple of things that I was not planning to do. And for that, I need to change slides. So I will unshare for a second. Will you unshare? So let me just open up another version of these slides that has some things I skipped. There you go. No. Yes. Hello.
Yeah, we can see.
All right.
Yeah.
You should be seeing my slides again, right?
Yeah.
Okay. This is a different version of the slide that has some material that I was planning on skipping. But we have plenty of time, so let's do this. So these are the parameterized Ackermann functions that we did mention, and then I mentioned that we had some base change maximal numeral forms, and I said that they're very complicated. Now, they're very complicated, but it doesn't matter that they're very complicated, because when you have the result that every Goodstein walk is finite, you don't have to mention complicated normal forms at all. You say, look, you have the Ackermann function, you write things down using the Ackermann function, you do base change and so forth. That will always be terminating. That is independent independent of ATR not. The fact that you use complicated normal forms now becomes just part of the proof and just goes into the background. And so you get a much more natural independence result than if you have to spell out what these normal forms are, at least in this particular context, where, as you will see, they're very complicated. So what is the goal? So you have you fix your base K. I'm going to write Ackermann AB instead of Ackermann AKB because K is not going to change for the time being. The goal is to write M as some value of the Ackermann function plus a remainder. Once you do this, then you recursively also write the remainder and the A and the B in normal form. But first, you have to choose how M is represented. So this is very similar to the story when we were writing numbers in base K using the exponential. First, you choose what the exponent is, and then you check what the remainder is. And once you've done that, then you recursively write those things also in normal. Okay, so the idea is to approximate M with the Ackermann function, but we're going to have to do this more than once. So first, you choose a value A1. That is the biggest one that still gives you something below M. So basically, if you have a fat branch of the Ackermann function that gives you values below M, you want to exploit that because you can imagine that bigger branches will grow more after applying base change, because now a bigger branch is a k-fold iteration of a smaller branch, and if you raise to L, now you're getting an L-fold iteration. So the big branch is getting a lot of explosion when it gets raised. Okay, so you choose the biggest branch you could possibly use, and then of course you choose the biggest B that you could possibly use, and then you can say, okay, we're done. That's our normal forms, but no, that would not be base change maximal, and we also have some papers in that with Andreas and with Oriola, a student of ours, and you get all sorts. You always get termination no matter what normal forms you use, because all Goodstein walks to terminate, but you could get a lot less proof theoretic strength if you don't use right normal. So these normal forms, if you just stop here and say, I'm going to call it a day, I'm going to write M, and then the remainder is just whatever's left over. Yeah, you're going to get independence for something a little bit stronger than PA. Basically, you get something like ACA not plus, if you're familiar with that. Which, since I did talk about ATR not, I could say what it is. It's, instead of saying that if you have any well-ordered, then it's Turing jump exists, instead you just say that the omega is Turing jump exists. So that gives you something in between PA and ATR not. All right, but what's the problem here? The problem is that our first approximation might be much smaller than it. You might still be able to sneak another branch of the Ackermann function. So M1 is this thing. You might still be able to, for example, apply A0 to M1 and still get a value less or equal than M. You say, okay. So this big branch is already living inside M1. So that's good. Now I could apply A0, but maybe I could apply an even bigger branch. We apply the biggest branch that we can apply to our first approximation. And then we, of course, make B2 as big as possible. So what's happening here when we do base change? Well, we want to exploit this big branch that's over here. But that's fine, because the big branch is still going to live inside the B2. So that's why we're getting a big value under base change. But this A2 will make the value even bigger. So this A2 helps as well. So we keep going. And when do we stop? Well, M is in normal form written like this when we've done this process as many times as we can until we can not fit any more branches of the Ackermann function and still get a value smaller than M. And these are the base change maximal normal forms. As I said, these are quite involved. If your independent statement will be, hey, if you do this complicated operation, then you get a Goodstein process that's independent of AT or not. It's an interesting independent principle. It's reasonably natural, but it's when you're looking for nice examples of Gödel incompleteness, simplicity is valued. And this, I would not say that this is a simple statement, whereas the statement, hey, every Goodstein walk based on the Ackermann function is finite, you can explain that in much fewer words and with and much less time. Okay, so let's go for some more bonus content. Right, so these are the results. In summary, the sandwiching normal forms are maximal under base change. When we define Goodstein walks, then they the minute infinite time, no matter how we write numbers using the Ackermann function. So what goes next? There have been two families of fast-growing functions here. On the one hand, we have the Ackermann functions, which grow fairly fast. And then on the other hand, we have, well, when you say fairly fast and really fast and things like that, I mean, all of these are producing values that are much bigger than anything that fits in the universe. So, yeah, the Ackermann function already will very quickly exhaust how many particles you have in the observable universe, but even that will be dwarfed by these fast-growing functions. So now what do you say? Well, what if instead of taking the Ackermann function and then using that to produce an independent result of strength gamma naught, what if we start already with these fast-growing functions and use these to produce independence results? So we use this as a notation for the natural numbers. So here's just a quick reminder of the fundamental sequences. We were using +1 there for what I'm doing right now. And you could go either way. The point is to choose something. And now, now we're going to extend these functions so that what I put inside, so that the argument here is not a natural number, but is in fact any ordinal, still below epsilon 0, but anything we want. So what do we do here? In fact, this for natural numbers, it's very tame. It's just going to be the successor function. But how do we compute this function on a proper ordinal, on an infinite thing? Here's what we're going to do. So you have an ordinal below epsilon 0 that, I don't know if I put it in the slides here. It's not here. When you write a number in Cantor normal form, it has some coefficients. So it could be omega times 3 plus omega times 2, etc. So the 3 is a coefficient, the 2 is a coefficient. This MC is just the biggest coefficient that exists. So basically, we define these versions of the fast-growing functions that you take an ordinal. All right, if the ordinal doesn't have any finite part at the end, then all you're going to do is you just return the maximal coefficient. That's fine, that's all you do. But otherwise, you're going to apply the operation you already had to the predecessor. So that's just step 0 in our construction. What this K will do is that we're going to iterate this construction in a certain way. What certain way is it? So you have your ordinal. You've already computed this thing. you're going to use that as an argument for the fundamental sequence and compute your previously constructed function to the result of that fundamental sequence on the omega alpha part. Why on the omega alpha part? So the fundamental sequence all really makes most sense when we apply it to a limit. This ordinal is a limit plus a natural number part. So we want to sort of ignore that and apply fundamental sequence only to the limit part where we're going to get something actually interesting, right? So you get a value, and now that becomes the argument of the fundamental sequence and so forth. So you get a sort of nesting where the nesting occurs in the fundamental sequence part, and you stop after k steps. So this, I mean, these things are just humongous. They grow faster than the. It's already based on epsilon 0, but they grow even faster than the Hardy functions because the value at which you're evaluating the fundamental sequence is also growing very, very quick. So if you got a bit lost in the details here, the short story is that these are just parametrized versions of something a little bit like the Hardy function, but that grows up a bit faster, and it grows faster and faster as you vary k. So now what we're going to do is we live in two worlds. We have the ordinal terms, and we have the number terms, and this is very, very, very nice because you take any ordinal below epsilon 0 written in the usual ways. But the only way to write down natural numbers is by applying this function a. And the reason that works is because since I'm basing this a function on the successor, I can guarantee that every natural number is going to be in the range of this a function. Except for 0, but here we don't need to write 0 this way. All right, so in this setting, we also have a similar phenomenon. You take a natural number, you write it as the value of a function applied to an ordinal. You raise the base, which in this case means that you change every coefficient you see here by its property, its base change. So this gives us an independence result for ID1. What is ID1? ATR not allows us to iterate arithmetical operations along previously constructed well orders. ID1 allows us to iterate them over large enough well orders so that we eventually reach a fixed point, and that gives a lot more strength. So how do we do this? We identify the base change maximal normal forms. We have an ordinal assignment, which now involves some uncountable ordinals. So this is something a bit messy that I'm not going to get into too much detail here. And yeah, now based only on, so based on functions that turn ordinals into natural numbers, we obtain the next layer of Goodstein processes that now gives independence for something much, much stronger than ATR naught. So let's stop sharing here. I'm going to switch again to the previous slide. And at this point, I still have some time, but I'm going to stop soon because now I've talked about most of what I wanted to say. Right, so I'm sharing. Right. So I'm just going to say some concluding remarks. This was at the end. Admittedly, the last part was a bit more sketchy and we saw it very quickly. But we can use families of functions to write down natural numbers, and they lead to Goodstein processes. In particular, we can use fast-growing hierarchies already as our notation for natural numbers, and these give very, very strong Goodstein principles. So what I talked about was this parameterized version of the Hardy function for epsilon 0 that leads to independence of ID1. Again, that's already quite a strong theory. It's quite a strong theory, but it still falls below below what we call the big five theories of second order arithmetic, where the strongest one is pi1 comprehension, whose ordinal is quite a bit bigger than this guy. So the Beckman-Howard ordinal is the ordinal of ID1, and it's a curious ordinal because now you start to define ordinals, countable ordinals, based on uncountable ones and collapsing them back down. So things get trickier and trickier as you go up this hierarchy of ordinals. So now this ID1 result shows that in principle, fast-growing hierarchies can be used to define the Goodstein process and not only to calculate its termination time, and that, at least in principle, it gives independence for strong theories. So Oriella, which is our student, is working on ordinals bigger than the Beckman-Howard ordinal. Well, actually, she is working on the fast-growing hierarchy for this Beckman-Howard ordinal, which now gives termination time that can be described in terms of an even bigger ordinal and so forth. The goal being here a little bit getting to pi1 comprehension and to something called pi1 transfinite recursion, which is similar to ATR not, but now we allow universal quantification over sets in this in the property for the recursion. So as I said, this is all the material I had. I got quite a bit farther than I expected and still have plenty of time for questions, so I guess that's a good thing. And I just want to thank you for your attention.